Suppose we have this function, f of x equals x squared minus 9 over x plus 3. We know just by inspecting this function that x can never equal negative 3 because the function wouldn't be defined there. And therefore, this function, f of x, does not have a y value when x equals negative 3. Now, since we know that's the case, we know the function is not continuous there. So the next thing to do is to try and find out what kind of discontinuity the function has. Okay? So we do that by checking the limit. So we're going to look at the limit as x goes to negative 3 of this function. But luckily, that's not a difficult limit to figure out. We can factor and cancel. And if we do that, we get x minus 3 times x plus 3 over x plus 3. We can cancel x plus 3. And you'll notice that now I can plug in negative 3, while before I could not. So if I do negative 3 minus negative 3, I get negative 6. Okay. So the question now becomes, what type of discontinuity does this graph have when x equals negative 3? So this function has a pod at x equals negative 3, y equals negative 6. So on the graph, as a matter of fact, we can do pretty well with this thing. We know exactly what this graph looks like. The graph of x minus 3 is a line with slope 1 and y-intercept negative 3. And so here's negative 3, and it's got a slope of 1. So we go up 1 over 1, up 1 over 1, up 1 over 1, and so forth. So the graph would look like this until we got to a point on the graph where x equals negative 3. Because we know there it doesn't have a y value. But we know the limit existed. We know that on the left side of negative 3 and on the right side of negative 3, in both cases, y was equal to negative 6 or close to negative 6. So this graph has a pod or a point of discontinuity. Okay? Now, you may have noticed the title of the lesson today. The title of the lesson is Fixing Removable Discontinuities. Okay? Pods, points of discontinuity, are considered removable. The reason to consider removable is that we can fix them. All we need to do is fill in this dot. If we filled in that dot, then clearly I would be able to trace right over this function and never have to lift my pen. So instructions for problems like this might be, write an extended function or a piecewise function that is continuous at x equals negative 3. So to do that, here's what I'll do. I'm going to use a new letter. I'm going to say g of x. Oops, sorry about that. G of x equals, and the function is x squared minus 9 over x plus 3. Whenever x doesn't equal negative 3, we can write that two ways. We could write x doesn't equal negative 3, or we could have written negative infinity to negative 3 union 3 to infinity. You should just understand both types of notation. Okay? And then what we're going to do is, when x actually equals negative 3, we're going to ask ourselves, what y value do we really want to have then? We would like y to equal negative 6. We know that because on the left and the right sides of x equals negative 3, y was getting close to negative 6. So I just want this dot to get filled in. This thing we have here, this thing I'm circling in blue now, is called an extended function or a piecewise function. You can use either language to describe that. And what's special about this function, it is continuous at x equals negative 3. Where the original function that we were given at the beginning of this story, this one, is not continuous when x equals negative 3. Okay? And that's sort of the goal here. Can we take functions and rewrite them and make them continuous at a particular value of x? So let's consider another example. Let's look at f of x equals x cubed minus 1 over x squared minus 1. Now, clearly, this function is not continuous at x equals 1 or negative 1. So the first thing I'd like to do is try and find where f of x has removable discontinuity. So let's do that first. So we can tell just by looking at the denominator and setting it equal to 0 that this function is not continuous at x equals plus or minus 1. So that means you need to check two limits. You need to check the limit as x goes to 1, and you also need to check the limit as x goes to negative 1 of the same function. Now, it's helpful to reduce this function a little bit before you get started. The denominator is easy enough. That's just the difference of two squares. But for the top, sometimes people forget that there's a way to factor a difference of perfect cubes. So let's remind you of what that is. Perfect cubes can be factored in the following way. So a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So we can use that right here, and here we go. So if you look at this expression, x cubed is like a cubed, and 1 is like 1 cubed. So it becomes x minus 1 times x squared plus 1 times x, or just x, plus 1 squared, which is 1. So there you go. That factors very nicely. So this reduces now. You can cancel these out. And then each of these limits now down here becomes a little simpler to look at. It's x squared plus x plus 1 over x plus 1. And then over here you have x squared plus x plus 1 over x minus 1. Well, what you'll notice is, at least in this limit on the left, I can actually plug 1 in now. That I couldn't do that before, right? And if I do that, I get 2 on the bottom and 3 on the top. So the answer to the first limit is 3/2. So what does that mean? It means that f of x has a pod at the point 1, 3/2. So that's a removable discontinuity. We'll be able to fix that one. Now let's just take a look at this other limit for a minute. You'll notice we didn't luck out quite so much here, because we can't just plug in. That's plus 1. Oh, I got nervous for a second there. Whoa. Continue. Here, if we plug in negative 1, it's still undefined. So you could check left and right, but what's going to happen is this. If you check left and right, you're going to find out that you get a vertical asymptote. So this is considered non-removable discontinuity. So that can't be fixed, but this one can. So don't expect all discontinuities to be discontinuities that you can repair or fix. So here's what we can do. We can write a new function g of x, and we can say that it's going to equal x cubed minus 1 over x squared minus 1 for the following. From negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. And then we know that at x equals 1, we can fix that discontinuity by making y equal to 3/2. So this thing here is an extended or a piecewise function that is continuous when x is equal to 1. It is continuous at x equals 1. It's not continuous at x equals negative 1. And the reason why is this limit doesn't exist or is equal to infinity. Okay? And because of that, it has a vertical asymptote on the graph, and therefore it can't be repaired. So let's just remind ourselves of what can be fixed and what can't be fixed in terms of discontinuities. So here's your graph. Something like this, a pod, I can simply make this continuous by filling in the solid dot. So a pod is considered a removable discontinuity. However, if you consider a jump discontinuity, something like this maybe, the problem you have here is that even if I fill in one of these solid dots, I can't fill in both of them. I can fill in one of them. Even if I fill in this one on the top, I still have the problem where the limit on the left and the limit on the right are not the same. So I can't quickly fix this discontinuity. So this is considered non-removable. And then lastly, any kind of vertical asymptote is non-removable. So for example, say this is your VA, and they both, even if they both go up together, there's not a single dot I could put on this graph and then make everything connect together smoothly. Because technically these two pieces of the graph never meet. They just climb infinitely high. This one's probably more obvious. That one's going up, that one's going down. They're never going to meet. I can't put a dot on the graph that makes them meet. So these are, again, non-removable discontinuities.